Welcome back to the course of Special Relativity. Today we are going to talk about some examples of evidence that by the end of the 19th century pointed at the need for some new physics. There were several observations at the end of the 19th century that were pointing to the problem to agree classical mechanics and electromagnetism, light propagation. And I'm going to talk about two of them that make it clear that changes needed to be made. I will talk first about astronomical observation of binary stars and then about the famous experiment by Michelson and Morley. More than half of the stars we observe in the universe are actually binary stars. These are two stars revolving about a common center of mass. For the sake of simplicity, let's consider that we have one system where one of the stars is more massive and basically we can say that the other one just revolves about this first one. We are astronomers on Earth observing this binary system. What we observe is the light that left the binary star, each one of the stars, a while ago. Star B revolves the counterclockwise direction as seen from this scheme. When star B is at point 1, light was emitted that is going to be captured by our telescope. When star B is at point 2, the same happens. We call C1 to the speed of light emitted at 1 and C2 to the speed of light emitted at 2. Depending on the distance from the binary system to the Earth, it could happen that light coming from 2 arrived at Earth before light coming from 1. This is something we do not observe as it would look like we are seeing the future of the star before it's past. But maybe this is actually happening, but stars need to be so far away that those binary systems are so far away that light has not yet arrived. Let's calculate then the distance at which they should be. So the distance at which we should observe light from 2 before light from 1, at which distance those stars should be from us. The speed of light emitted by the moving star B at 1 would be the speed of light would have if the star was at rest, c minus the speed of the star V. The speed of light emitted by the moving star at 2 will be c plus V. Speed is the distance over time. I'm going to calculate the time that light needs to get to Earth both from 1 and from 2. Time is equals to distance over velocity, and I want to find the condition for both beams of light to arrive at the same time at Earth. Because light at 2 is emitted half a period later, we can write T2 as T1 minus half the period of the rotation of the star. I will substitute T1 in the second equation and will solve for the distance at which the binary system would need to be so that we observe light from 1 and from 2 arriving at Earth simultaneously. We can relate the period with the radius of the orbit using the expression that the speed of the star is 2 pi r divided by t, be t the period, the time that the star needs to revolve once around the other star, star B around star A. Then we can rewrite this result, and I will divide up and down by c squared, and I get this final result. Is this a large distance? Well, let's substitute some reasonable numbers here. The speed of the star could be 60 kilometers per second, something reasonable, and radius of the orbit 10 million kilometers. These are very common numbers in astronomy. We substitute and we get about 40 light years, just right here in our nearest neighborhood. Take into account that the Milky Way is about 100,000 light years in diameter. If this was true, we would have already observed this phenomenon, and we haven't. So we've got a problem here, Houston. A problem that we will solve soon. See you in the next lesson, and may the science be with you.